Sir, live event started. You can go on.
Okay. Okay, sir. A very good morning to respected HOD sir, invited speakers, senior faculty members, my colleagues, and all the participants. I welcome you all in the webinar on the art of learning semiconductor devices, PN junctions, MOSFETs, and memristors, which is organized by Department of Electronics and Communication Engineering, Madanapalli Institute of Technology and Science. This webinar is going to address a few basic concepts of semiconductor devices, particularly PN junctions, MOSFETs, and memristors. The objective of the webinar is to motivate the students towards discovering new ways of understanding devices in general through the various concepts. Now I request our HOD sir to address a few words regarding the webinar. Hello.
Hello.
Yes.
Good morning, 100% here. First of all, I would like to thank our Rupam Goswami, Department of Electronics and Communication Engineering, Tezpur University, Assam, for accepting our invitation and ready to give webinar on the art of learning semiconductor devices. Thank you very much, sir. So usually our department organizes various seminars, workshops, and guest lectures. So this time also we are organizing through this online. So because of this COVID-19, we could not organize anything. So because so now we are organizing. So this will be helpful for our students and also other college students. So nearly 600 students are already participated. They are already joined in this webinar. So I thank all the coordinator, Shanidul sir and Sarwesh sir. Thank you very much for your presentation also, sir. Thank you, sir.
Thank you, sir, for your valuable words. So now I am going to introduce today's invited speaker, Dr. Rupam Goswami. So presently he is associated with Tezpur University as an assistant professor in the Department of Electronics and Communication Engineering. His research interests include simulation and modeling of semiconductor devices like FinFET, TunnelFET, and memristors. He has completed his BE from Assam Engineering College, Hoque, and MTech and PhD from NIT Silchar. He has contributed many notable works in the domain of semiconductor devices like TunnelFET, FinFET through the various reputed journals such as IEEE Transaction on Electron Devices, IEEE Transaction on Nanotechnology, IEEE Transaction on Ultrasonic Ferroelectrics and Frequency Control, and IEEE Sensor journals. And apart from this, various reputed journal of Springer, Elsevier, and Wiley. He has 30 publications in peer-reviewed international journals, conferences, and book chapters, and he has filed 2 patents. Presently, he is working on 3 research projects sponsored by Government of India. And apart from this, presently he is an editor of Guwahatian e-magazine also. So now I welcome Dr. Rupam Goswami and request you to deliver your valuable talk on semiconductor devices. Thank you.
Thank you, Dr. Shanidul Hoque. So I think I'm audible, right?
Yes, yes.
Okay. So I also thank HOD sir for inviting me and giving me this opportunity to present this webinar. And I have chosen this topic because of trying to go along the basics and also trying to enjoy the different perspectives of semiconductor devices. It is not possible to cover the entire aspects of all these devices, particularly PN junctions and MOSFETs, because these are actually very vast in their entire domain. So we'll just try to address a very few important points, and take this not just as a course, take this as something which you can enjoy as you move along the lecture. And we will try to make this as simple as possible. We'll try to use less equations, fewer equations, and we will more concentrate on how you can proceed from today's lecture. It should not end here. Whatever you learn here or whatever you are on the verge of learning from this lecture, I wish to see that you continue this pursuit of learning these devices. So without wasting much time, we will be moving into the lecture, and I request you to put on your headphones or earphones so that you can listen to the lecture well. And also I'm switching off my camera because it is eating up a lot of bandwidth. So I think I'm audible, right? So there's no problem.
Yes, yes.
Okay. So first of all, this webinar on the art of learning of semiconductor devices. So I have named it the art of learning semiconductor devices because most of the times, whenever we look into a semiconductor device, we get so much confused with the equations, the continuity equations, the drift and diffusion, that we almost try to leave that concept there because it's so much confusing. But if you look into the working of devices and try to look at it from different perspectives, so you can say that there are different ways of understanding the same device. So you can understand a device right from a very basic analogy to the use of equations. So you should not directly jump into the equations which you are trying to solve or which you see in your textbooks. But before that, you should know the qualitative aspects of these devices. So therefore, here we will be discussing the philosophy of approach rather than taking up a very technical topic and discussing on it. So today is June 29, and today's day is special because today is the National Statistics Day. We'll move into the next slide. And once again, I thank Magnapell Institute of Technology and Science for giving me this opportunity of presenting this. So June 29, 2020 happens to be the National Statistics Day, and June 29 was the date of birth of Professor P.C. Mahalanobis, one of the very stalking personalities in the field of statistics and mathematics. And he was the founder of the Indian Statistical Institute at Calcutta. So it's known as Indian Statistical Institute Calcutta because of the time at which it was formed. And Professor Mahalanobis is known for many of his various proposals, the most particularly being the Mahalanobis distance, which is used to compare two statistical data sets. And he was a fellow of the Royal Society, and so today's day is dedicated to him. So we are proud of such an Indian who could contribute to the world of statistics. And after that, before moving into the lecture, I would like to share a video with you. This video is by Samsung, and it describes a new transistor structure. Obviously, it is not that new as of now because this video was released, I think, a year or two back. So we'll just try to look into the video before proceeding into the main part of today's lecture. So is the screen visible? Shanidul, is the screen visible? Dr. Hoque? Dr. Shanidul, is the screen visible?
Hello?
Yeah, is the screen visible?
Yes, sir, it's visible.
Okay.
ನಮಸ್ಕಾರ. ಕೋವಿಡ್-19 ಅನ್ಲಾಕ್ ಪ್ರಕ್ರಿಯೆ ಈಗ ಪೂರ್ತಿ ದೇಶದಲ್ಲಿ ಆರಂಭವಾಗಿದ್ದು ಅತಿ ಅಗತ್ಯವಿದ್ದರೂ
Yeah, you can. Hello? You can say actually my system got hanged. Hello? Yeah. Sometimes Rupam may ask whether that is working or not. Okay?
Okay, so I think the video was clear. So it described, it showed a part of Samsung's one of the most novel structures, the multi-bridge. Yeah. So is the presentation visible?
Yeah.
Yeah. So this multi-bridge channel FET is actually a gate-all-around structure, and we normally work on these devices whenever we try to model them. The advantage of gate-all-around structure is that you can surround the channel from all the sides, so that you have better control over the entire channel. So that's the advantage of the gate-all-around structure. However, we'll not be discussing this in today's lecture, but this was just an overview, because most of you must have heard about FinFET technology. So they are also available in your mobile phones. So this MBC FET is now going to be the next phase of the devices of the devices industry, and due to its very versatile nature of being scaled or stacked up laterally, so it will occupy very lesser area. And as you know, that area is one of the most important ingredients of the semiconductor recipe. So therefore, this was a video just to show what the things are and what can be done on the field effect transistor devices. So now let's proceed into the lecture today. So these are the key contents of today's lecture. So we'll start with a few basic concepts. Most of you must be knowing them, but I hope these are necessary to start with the lecture. And then we'll move into the p-n junctions, which is obviously a nature's beauty. In fact, every device has its own beauty, but p-n junctions, because they are considered to be the most fundamental devices in learning semiconductor devices. So I attribute the term nature's beauty to the p-n junctions. And then we'll move into MOSFETs, and we'll look into the short channel effects and the Moore's law. We'll not discuss the short channel effects in detail once again, because it is not possible to cover in this short lecture, but we'll try to stress on the key points. And then we'll move into the memristors, and finally we'll try, if time permits, we'll try to understand what we can do with NanoHub, which is a very account-filled website where you can simulate your own structures, and you can understand very basic concepts of semiconductor devices through very simple graphical user interfaces. So there are plenty of tools on this particular platform, and through them you can easily learn and understand devices. So now moving into the basic concepts, these are purely basic and purely preliminary concepts. So therefore, although you may be knowing this, but try to bear with this particular part of the lecture. So first of all, energy, potential, and electric field. We are so familiar with these terms whenever we deal with any semiconductor device, and we try to evaluate or understand the principle of operation of a device by using these terms. And most of the times, although these seem very convenient and very easy in some matter, but we try to lose the focus somewhere while going from one point to another. So this part will simply try to bring up those things as we move through the p-n junctions. So first of all, say for example, you are having an n-type semiconductor, okay? So the n-type semiconductor is doped with impurities which can donate electrons to the particular crystal. And we assume that this is a silicon crystal for simplicity, because we are so familiar with the parameters of silicon. So as you can see on the diagram, you have the edge of the conduction band, the edge of the valence band. So the first point which must come into your mind is that the straight lines which you see, which are labeled as EC and EV, these are not conduction band and valence band. These are the edges of the conduction band and the valence band. So which means if I'm talking about EC, so my conduction band starts from there. And if I'm talking about EV, my valence band ends at that particular edge. So these are some of the basic things which students make mistakes often while writing their answers or trying to understand the device. Secondly, you have seen the EF, which is your Fermi level. So this is the Fermi level for your N-type semiconductor, and you also have your intrinsic Fermi level, which is EI. So basically, the EI is assumed to be located centrally in the semiconductor band gap, which is the forbidden gap. So that is the difference between EC and EV. And why centrally? Because the intrinsic semiconductor means that the concentration of holes and electrons are equal in that particular crystal, and therefore we try to put the intrinsic Fermi level at the center of the band gap. Now, in this particular diagram which you see, we have not applied any potential or say any voltage anywhere in the crystal. And suppose if I try to apply a voltage which is shown on the right hand side of your screen, say I'm applying a +2 volt on the right hand side and the 0 volt on the left hand side. So what do you see? You will see that the bands will shift, right? So why do these bands shift actually? So the basics of everything in terms of the energy bands come from the Poisson equation, which is actually a derivative of the Gauss's law. So the Poisson equation can describe most of the phenomena in your normal crystals of semiconductor devices, apart from the quantum mechanical effects. Because for the quantum mechanical effects, you need to incorporate an additional term. So therefore, we'll not try to move into the quantum effects because that is again another topic for a lecture. So we'll just try to focus on this. So here, the energy bands towards the right, if you see, has been pushed downwards, and on the left has been pushed upward. So although we know these kind of things, we try to relate them with the difference. So if you see here, you can see that on the right hand side was your high potential, and on the left hand side of your N-type, you have a very low potential. Now, how is potential related to the energy? So energy is actually the negative of the potential. It is minus Q times the potential which exists, right? So therefore, you will be having an opposite effect. So if you have applied a positive here, so instead of going up, your bands will move downward, right? And since there is a continuous supply of the voltage and the electrons or carriers to this N-type crystal, so all the bands will bend in this particular manner, right? Now the next point is, what is the direction of the electric field? So this is a very rarely encountered term whenever we are dealing with semiconductor devices. We are normally so satisfied with the band diagram that we do not try to look into the direction of the electric field and what is its relation. Or if I put it simply, what is the simplest way to know the direction of the field? So the direction of the field will be from right to left, right? Because if you place a positive charge here, a unit positive charge, so it will try to drag along the left direction. But how to evaluate it in terms of the band values which you are seeing on the screen? So if you look here, the electric field is given as minus d phi by dx. So phi is your electrostatic potential or your potential, and phi is again related to the energy by something like this. So it is energy by Q, negative of the energy of by Q. And when you eliminate the negative signs, you reach at something like this. So if you see at the final expression, the electric field is directly proportional to the slope of the intrinsic Fermi level. So your intrinsic Fermi level goes like this. So your electric field will point in this direction. Okay. So instead of the intrinsic Fermi level, you can also substitute the conduction energy band H. So because these are relative concepts, so you can replace either of these terms because we are concerned only with the slope. Okay. So this is one of the key points of looking into the very basics of a device, right? Next, what are quasi-Fermi levels? So every one of you know that, and you have heard of Fermi levels, and you must have also heard about quasi-Fermi levels. Whenever you encounter a p-n junction, you know that the voltage drop across the depletion region is equal to the addition of those quasi-Fermi levels of quasi-Fermi potentials of the p-type and the n-type regions. Now, if you want to understand why quasi-Fermi levels are important, why are we not so satisfied with a single Fermi level? What's the problem with a single Fermi level? That's the question. So suppose again we take up that n-type semiconductor crystal, right? And we try to shine some external excitation through some optical phenomena on that particular crystal. And you must know that whenever we try to make photons incident on a semiconductor crystal, it generates electron-hole pairs because it breaks the bonds, right? So say we are taking that particular case, and here we are assuming that the light incident is uniform throughout the crystal surface, and that the generation of electron-hole pairs are uniform throughout the length. So in that case, your Fermi levels, you will see that there are two Fermi levels, one for the n-type carriers or the electrons, and one for the holes. So EFN and EFP, they denote the quasi-Fermi levels for electrons and holes. So why do we need this? So let us try to look at it from a very simple mathematical understanding. So suppose the doping of my n-type semiconductor is 10 to the power 15. And assuming that it is silicon and it is at room temperature, I can find out the concentration of minority carriers. So it will be around 2.25 into 10 to the power 5, which is very low, right? Now, due to the incidence of this particular photon, the striking of the photons on the crystal, so I find that the generation is, say, this particular action or event generates 10 to the power 12 per centimeter cube of electron hole pairs. So since you are generating electron hole pairs, therefore the concentration of electrons as well as the holes due to this particular event are equal. Now you try to calculate the new values of your minority carrier and your majority carriers, right? So P nu is your new value of your minority carrier. So it was earlier, it was 2.25 into 10 to the power 5, and now it is 10 to the power 12, because if you add up, you are adding, there are more holes now, so you are adding them up. So it becomes 10 to the power 12 per centimeter cube. On the other hand, if you look at the electron concentration, or say the majority carrier concentration, so it stays at 10 to the power 15. Okay, so there's a printing mistake here. It should be 10 to the power 12. So just try to understand that this is n photons. Okay, so this is 10 to the power 12 plus 10 to the power 15. So it must give you 10 to the power 15. So it stays at that particular level as which it stayed earlier. So if you see, there is a very greater jump for the minority carriers from the order of 10 to the power 5 to the order of 10 to the power 12. So one single Fermi level is not sufficient to explain the nature of this presence of new very high increase of holes. Therefore, you need two Fermi levels, one for the electrons and one for the holes, to explain the insurgence of these carriers into the crystal. That is the importance of quasi-Fermi levels, right? And another point, a very interesting point, due to this particular incidence of photons, you are having this development of quasi-Fermi levels. And this concept, now you can use this concept to your PN junctions and MOSFETs whenever there is a requirement or whenever there is a very high increase in the minority carrier. So if there is a phenomenon where there is a high increase of minority carrier due to some excitation or due to some internal phenomenon, so in those cases, the quasi-Fermi levels are of great importance. Okay, so these are the two concepts which I thought would be very appealing to you. And once again, just pardon the error here. So it's for your electrons, it must be 10 to the power 12 plus 10 to the power 15. So it's just a typographical error. So just ignore this error. So, but still, your concentration of majority carriers remains at 10 to the power 15 per centimeter cube. Okay. So there is a very high increase from 10 to the power 5 to 10 to the power 12. So therefore, you need two different Fermi levels to explain the effect. Now moving into p-n junctions. What comes to your mind whenever you think of a p-n junction? So you just try to recall that diode circuit symbol, right? The forward arrow with a straight line at the end of that particular cathode. So that's the ultimate thing which comes to your mind, and the forward drop of 0.7 volt for silicon and near about 0.3 volt for germanium. So those are the things that come to your mind. But do you know how these p-n junctions were discovered or invented? So let us now take a very brief understanding of how things happen in and around the p-n junctions. Okay, so whenever we talk of p-n junctions, the ultimate thing which comes to our mind is serendipity. So if you remember, I tell to my students in my classes that most of the discoveries and inventions in semiconductor devices, and say in any levels of science, also most of them often come from accidents, and they are beautiful in terms of the results which they see. They lead to new discoveries and inventions. Serendipity is such feeling when you discover something by accident. Okay, and Ohl, so Russell Ohl was the person who first proposed the idea of the p-n junction. And in fact, the idea of p-n junction came some moments later, but at the initial stage, the concept of solar cell came, and then the p-n junction concept followed. So although this was a very simultaneous event, but the main research he was doing led to the development or led to the patent for solar cells. So if you see here, so in the mid-1930s, Russell Ohl, an electrochemist at Bell Telephone Labs, he began investigating the use of silicon rectifiers as radar detectors. So during that time, vacuum tubes were considered to be the most significant electronic elements in the semiconductor industry. And they were trying to experiment with other rectifiers like silicon, with crystals actually. And at that instant, Bell Labs tried to say, when Russell Ohl repeatedly failed, that they would be closing down the crystal research on the silicon, and they will be continuing with vacuum tubes. But Russell Ohl was a bit adamant, so he was not willing to leave that particular area of research because he was pretty much interested into researching for materials. So he tried to move into the purification of silicon, and he began experimenting this particular cases. So he was almost fed up of his particular experiments because they did not yield any result. So on 23 February 1940, when Russell Ohl was in his lab, so he tested a small silicon slab that yielded very strange results. So when exposed to bright light, so there were incandescent lights on his in his laboratory, and some reports even say that there was a crack in his window through which the light fell on his particular device or the silicon slab. So ultimately, when exposed to bright light, the current jumped. So the current values, it increased considerably, and this led to the discovery of the photovoltaic effect that powers today's solar cells. But more importantly, what made the discovery and what is its relation to the p-n junction? So he realized when he saw this particular effect, photovoltaic effect on his silicon slab, he tried to evaluate this and he called his seniors. So Walter Brattain was one of his seniors. So if you remember, Brattain was one of the inventors for your transistors, the point contact transistors. So they were called and they tried to investigate this, and they found that there were different kinds of impurities on both sides of a very small crack which behaved as a junction. So ultimately, there's a junction, and on both sides of the junction, you have different carrier values. So therefore, it led to the development of this current whenever light fell on it. So it generated these electron hole pairs again, and so you saw a jump in the current. So this is Russell Hall, and it is attributed, the invention of this PN junction or the discovery of this photovoltaic effect is attributed to this gentleman. And now moving into the PN junction, first of all, let's get done with the preliminaries which are necessary. So basically, all of us know that a PN junction comprises of a p-type material and an n-type material, and they are metallurgically they are connected. Okay, so that's the idea of a PN junction, and the point or the coordinate along the length at which they are joined, or say they are they form a junction. That is actually the PN junction we talked about. Now, one side is highly doped with P, or say is doped with P-type materials. On the other side, you have N-type materials. So there's a diffusion gradient for both the kinds of materials once you bring them into contact. So the first instant, at the very first instant, the electrons will try to move from N-type region to the P-type region, and the holes will move from the P-type region to the N-type region. So this is a very common natural phenomenon. Whenever there is a gradient in distribution of anything, of carriers, of gases, of liquids, so whenever it finds a gradient, so it will move from the P-type or the N-type region into the other region. Now, whenever we are discussing this semiconductor devices, so when a gas particle moves from one region to another region, it does not leave anything from its entire element. But here, since you are using dopants, therefore if an electron moves from the N-type region to the P-type region, so it will leave behind a donor ion. Okay, so basically it's like the donor atoms are contributing the electrons to move into the P-type region. And due to this development, so similar things will happen on the P-type side as well. Due to this development, or due to this flow of majority carriers from one side to another, so you will be having a region which is comprised only of the ions. So on the P-type, you'll be having the acceptor type ions, which are negatively charged because it has given away a hole, so it will assume a negative charge. And on the N-type region, you'll be having a donor ion because it has donated an electron, so it will assume a positive charge. Now, if you look the picture which is present on the right-hand side of your screen, so the electric field, there will be an internal electric field which will be developed. So due to this internal electric field, this will prevent the further flow of holes and electrons from one side to another. So this is the beauty of the PN junction. So once it is brought in contact, it has the ability to form an electric field or an opposing force to prevent the flow of carriers. This is very evident, right? But if you look into it from the perspective of an invention or from the perspective of an effect, it is very interesting. So it tries to stimulate a self-generation of electric field due to nature's law of distribution of carriers due to the gradient, right? So now, due to this electric field, so there will be no further motion of carriers. So that's the thing, that's the picture you see in thermal equilibrium. So unless you apply a voltage across the PN junction, there will be no flow of carriers in the ideal sense, no flow of carriers because of this internal electric field. And whenever you apply a certain voltage, so remember, you are applying a voltage So you are applying a potential. So there will be an electric field you are applying. So due to that electric field, if the direction opposes the internal electric field, so it will be forward biased. And if the direction adds to the internal electric field, it will be reverse biased. So this is the entire picture of the p-n junction. Okay. Now the second question is, there is electric field in your p-n junction, and also there is a diffusion of carriers. So therefore, the p-n junction operates on the principle of drift and diffusion. So therefore, we say that the p-n junction has the ability to work on the principle of both drift and diffusion. Now, here, we are not talking of the minority carriers. So let's look at it at a very different perspective. So now the electrons, which were the majority carriers in your n-type, have moved into your p-type region, right? So the majority carriers electrons which were present in the n-type region now becomes your minority in your p-type region. And similarly, the holes now become minority in the n-type regions. And although we will not be discussing the derivation of the p-n junction current, because it will take almost like 1.5 hours for that itself. But I would like to stress on this point that minority carriers are one of the most important components of p-n junctions from the theoretical perspectives of derivation of current, because minority carriers are used in the derivation of these equations of current which you see for your p-n junction. Okay. So therefore, although we do not talk about the effect of minority carriers while explaining the principle of working of these devices at a very macroscopic level, just as we are doing now, but whenever you are going into the modeling aspect, so in that case, the minority carriers are very, very important for deriving your current. Okay. Now, let us try to look at this p-n junction from the perspectives of energy bands. Okay. Now, if you see, you're having a p-type material on the left-hand side, you are having an n-type material on the right-hand side of your screen, and E0 is the vacuum level. So after that, you have something called Q psi, but it is represented as Qx. So that is the electron affinity for that particular material. So what is this electron affinity? Very simply put, it is the energy required to move an electron from the edge of the conduction band up to the vacuum level. So the vacuum level is actually the level of energy at which the influence of that particular atom on that electron vanishes. So that can be called as a very layman definition of the vacuum level. Okay. I call it layman because vacuum levels are again of two types whenever we encounter in the devices. So what we are talking of is the local vacuum level. Okay. So we'll not go into that particular divisions of the vacuum level, but try to understand that it is the value of energy beyond which the influence of the atom on any particular carrier on an electron actually vanishes. And then you have your distance of the Fermi level to the vacuum level, which is your work function. So that is the work function you are saying, Q phi SP and Q phi SN. So it actually describes your value of the Fermi level from the vacuum level. So if you look into the diagram, what I mean to say is the vacuum level is used as a reference here for measuring all your distances of energy for the two types of materials, or say for any kind of material. So in an energy band diagram, whenever you start, particularly in heterojunctions, you don't see the importance of the vacuum level in homojunctions, but in heterojunctions, you see the effect or you see its importance more closely. So here, this is the picture which you see before contact, right? And once you bring this into contact, which means you are now trying to form that junction, so there will be a change in the concentration gradient. So my Fermi levels will try to attain a fixed level in equilibrium. right? So that's the property of this particular device. So it will always try to attain equilibrium. That's the property of nature. So if you are not sustaining that particular effect or say non-equilibrium, so it will always try to attain equilibrium. So that is true for all devices. Now, due to this change in the Fermi levels, so you will see that you will achieve a single Fermi level for the entire system. So entire system means here we are talking about the p-n junction as one system, and you can see there will be a change in the conduction bands and the valence bands, right? And this we will see why we are getting these changes. We'll see in the next upcoming slides. So basically, if you see now, if you look into the Fermi potentials on both sides, so you'll be able to see how they will contribute to the actual forward bias drop, or sorry, the built-in potential phi I. And if you are applying a forward bias, this will decrease, this barrier will decrease, so you will have more flow of the carriers. And if it is a reverse bias, this particular height of the barrier will increase. So it's just like what you see in conventional in your daily lives. If you have a wall, and if the height of the wall is high, you cannot jump it. So you'll require more energy to cross that barrier, right? So you will have more lesser chances to cross that barrier. So you'll have less current when you compare it to a p-n junction. And when your barrier height is less, or the height of the wall is less, so you can easily jump over the barrier because you require very less energy. So in that case, the chances of crossing the barrier increases, and so your current increases. That is the forward bias. And obviously, you have the breakdown as well in your reverse bias. So if you try to extend the analogy, it becomes a bit humorous. So even if the height of the wall is very high, if you provide very large energy, if you are a person with very high energy, so you can break the wall and move into the other side. So that is the breakdown which you see if you compare the analogies with a p-n junction. So now let's try to delve into a closer picture into this junction. So this is the p-n junction which we all know about, right? And so this is the distribution of the dopants which you see. If I try to plot them on a single plot, so I will see something like this. So positive Nd for the n-type, and for the p-type it's negative Na. And from there I am now trying to go into the depletion region. So see here, this is known as the depletion approximation for p-n junction. So what does this depletion approximation say? So basically speaking, in a very one-liner, the depletion approximation says that beyond the depletion region, there is no electric field which is generated in your junction. So the junction electric field does not cross your depletion region. So that's the very layman definition of your depletion approximation. And apart from that, if you go into the second point, so it depends on the minority carrier concentrations and the majority carrier concentrations which exist. But try to understand that the depletion approximation says that the electric field vanishes on the both sides of the depletion region. So therefore we have marked this like this. So since we do not have any mobile carriers within the depletion region, so in your diagram it is from minus xp to plus xn. So since we do not have any mobile carriers, so n minus p is made equal to 0, and on the other side you have the values as the doping concentration. So these are the neutral regions or the quasi-neutral regions which are defined. So ultimately, for a particular side, say I'm talking about the n-type side or the n-type region, it comprises of the space charge width or the depletion width and the quasi-neutral region. So in the quasi-neutral region, you still have available mobile carriers. So therefore you have a non-zero value here. And in the depletion width, you have immobile ions. So ions do not contribute to your current. Therefore, you have a 0 value here. And from there, I can write my charge density, which is Q times N divided by Q times N, where N is actually the value which you see here, ND or NA or minus NA. So depending upon that, I have placed this here. So rho here is Q times ND plus Q times ND, so it is positive. And on the p-type side, it is minus Q times NA. So this is important because you will realize this in the next slide when we go into looking into the electric field and the potential. Okay, so therefore we have gone step by step. First of all, we have tried to see the doping concentration which is available on both the sides. After that, we have tried to look into the available mobile carriers, and then upon application of the depletion region, we are trying to see that we have a positive value of rho here, or the charge density. Now, that particular diagram of charge density which we use, that we require because we are trying to look into the Poisson equation. So this particular screen will give you an idea of deriving qualitatively the electric field and the potential and then the Venn diagram directly from by looking at the distribution of carriers and without doing much mathematics. So you can directly derive your electric field and the electrostatic potential qualitatively, so without marking the maximum and the minimum values. So first of all, actually, you must be very confident of the trend which is appearing, how the electric field looks like. After that, the numerical values come into its place. So therefore, I am focusing more in this particular slide on deriving the actual, how the electric field will look like when you look across a particular dimension. So this is the charge density, and this is my one-dimensional Poisson's equation. So I hope you have come across this, but I'll just introduce to you the key parameters. So phi is actually your electrostatic potential, and basically we will be trying to derive that on the graph. Okay, and electric field here, this is the electric field. So you know that electric field is negative of d phi by dx. So therefore your second order differential reduces to a first order differential here, and that is equal to minus rho by epsilon. So epsilon is the permittivity of that particular material. So for silicon, it is 11.7 times epsilon naught, where epsilon naught is the permittivity in free space or vacuum, and rho is the charge density according to this region. So based on the value of this rho, your electric field will change, and so this particular potential will change. Okay, so now let's try to look into it and try to look into the picture first. So this is the electric field which you will see for this conditions here for this junction. So how to see that why is it decreasing like this and then increasing like this? Okay, so now if you see that, first of all, I will be trying to solve this region by region. So first I'll be taking up the p-type region. I will have to look into the p-type region. Then I will have to look into the n-type region. Okay. So first of all, I realize that my del E by del X is equal to minus Q NA by epsilon. So it is having a negative slope. So if it is having a negative slope, if I try to solve this, I'll be directly having a straight line, something like this. It is a straight line because this is a first order differential. Okay. So I'll be having something which is going downwards. Okay. So I'll end my drawing here. And after that, I will see what exists on the other side. So on the other side, I see that it has a positive value. So obviously, my straight line has to increase. And it is a very well known fact that at the junction, your electric field will have the same value. So if you know the trend on the P side, you know that it will decrease like this. It will come to a particular maximum value. And then from that point onward, it will again increase on the N side because it has a positive slope. So that is how you deduce the electric field plot by just looking at the charge density. Okay, and from here, obviously, from here again, if you look, so you can see that you'll have to integrate this, and since this is a linear slope, so therefore upon integrating, it will try to assume a quadratic type of nature. So on particularly solving this particular equation using all the boundary conditions, you will see a potential which appears something like this. Again, just try to remember that at the junction, the potential from your P side and the potential from your N side must have the same value. So using these very simple conditions, we can intuitively figure out what my energy band diagram will look like. But I would like to put a disclaimer here. Now suppose I flip my charge density profile here. What I mean to say is I put my N side on the left hand side and my P side on the right hand side. So what will happen then to my electric field profile? So your electric field profile will not then decrease like this. It will increase upward because N-type region will have this positive value here, right? So it will try to have an increasing slope here and then decrease. So both the things are different. So you will see that the effect of the electric field will appear something like this, okay? And finally, we'll be having the same value of potential plot. But now the question is, how will you go into the energy band from the potential? So we know that the energy band is negative Q times the electrostatic potential. So you just make a negative of this graph, you flip this graph and then multiply by Q. So you get the conduction band edge. If you get the conduction band edge, you will get the valence band edge, and also you will get the intrinsic Fermi level. So that is how you intuitively can figure out the entire energy band diagram just by looking at the charge density profile, or if we see just by looking at this p-n junction distribution. Okay, so we'll end our p-n junction topic here. We'll not go into the current profiles and we'll move into MOSFETs now, right? So I hope you are finding this interesting. Because the first challenge is that I'm not using any major equations while describing the devices, because I want you to understand that if you can explain a device qualitatively, then it means you have understood that particular device, because through equations you can plot that particular curve and explain it to anyone. But if you can explain a device qualitatively or intuitively, then that is the biggest advantage you have got, and it means that you have actually learned that particular semiconductor device. Now we will move into the MOSFETs, and as I have said, we will not discuss the output characteristics and the different working principle of MOSFETs. We'll try to focus on the short channel effects, because that is the point from where the industry is trying to break through and move into the other devices. Okay. So therefore, it is you must be very clear what is the single reason for short channel effects. But before that, again, let us try to look into the different interesting facts about MOSFETs. So basically, field effect in devices was filed in 1928 by Julius E. Lilienfeld. So he filed a patent for a device for controlling electric current. So you can see an image of his patent application, the first drawing on the right hand side of your screen. So he actually filed it in 1928, and I think he got it granted in 1933. So the point here is, you must understand, or you must know, that in 1947 and in and around 48, that was the biggest year for the semiconductor industry, right before Kilby invented the integrated circuits in probably 1960s or something. So this was important because the trio of Shockley, Burdeen, and Brettin, they invented the point contact transistor and the junction transistor, which are the foundations for your bipolar junction transistors, right? And in these two devices, they tried to file claims for field effect. While filing their devices, while filing for patent, they mentioned the claims for field effect in their particular applications, patent applications. But a total of 65 claims in that particular patent were rejected because of Lilienfeld's patent in 1928. So it is very interesting to see that Lilienfeld had actually invented something way before the evolution of the bipolar junction transistors, and he had also fabricated the structure. So it is quite interesting to see how inventions can occur before time, and it requires credit and time to understand these devices, and then finally develop a more viable device out of that one. So this is the reason why I have shown you this, and this is an important fact which you need to understand. And after this, the next question which comes is you are already so much familiar with the MOSFETs, but who invented the MOSFETs, or say what was the timeline behind the invention of these MOSFETs? So in 1956, so if you can see the timeline now once again, so PN junctions, they were invented in the 1940s, and after that came the bipolar junction transistors, and after that came the MOSFETs, which we are going to discuss now. So in 1956, these two persons, Atala and Kang at Bell Labs, they were working on surface passivation problems due to the surface problems in bipolar junction transistors. So during that time, they built this insulated gate field effect transistor, which is a very primitive version of your MOSFET. And their work did not get quite wide recognition and remained in the official papers of Bell Labs. So there are many stories behind this. And but they built actually a very primitive version of the MOSFET. In 1962, Hyman and Hofstein, they built the silicon ICFET again, and they are considered to be in line with the invention of MOSFETs. So they are considered, this invention in 1962 is like considered to be one of the very closest invention to the MOSFETs. So Atala and Kang. So, but whenever you are crediting someone, you must credit both the groups. So Atala and Kang at Bell Labs in 1956, and Hyman and Hofstein in 1962. So this is the story with the invention of MOSFETs. And you can find, if you look at the bottom of the screen, you can find the details in this particular reference here by R.G. Arns. So you can find it there. Now, let us move into the Moore's law a little bit before moving into the different parts of the short channel effects. So what is the Moore's law basically? So the Moore's law basically predicted that how the number of components per chip will decrease with time, right? So, but Gordon Moore, he just tried to predict this law by observing only 3 data points of different industries, and thereafter it became a law because it was felt that the Moore's prediction was very much required in the semiconductor industry. So you can find everything about Gordon E. Moore's law into cramming more components onto integrated circuits in this volume of electronics. You can see the reference at the bottom of the slide, and here he describes about how this is going to affect the economy of the semiconductor industry. So that's more important here, rather than just focusing on the Dennard scaling law and trying to relate everything with the working of devices. If we can understand that how the device industry is affected by the number of components per unit area, so that is more important for you. And whenever you are studying a particular device, it means you are studying it because it came into one of those historical timelines just to satisfy that Moore's law. Okay, so I'll not be going into much details here because we have the short channel effects to cover. And this is one of the statements from The Economist in April 2015. So basically, there is only one statement here which I would like to highlight, and it says that, and that a few years ago, when transistors 28 nanometer wide were the state of the art, chip makers found their design and manufacturing costs beginning to rise sharply. New fabs now cost more than $6 billion US. In other words, transistors can be shrunk further, but they are now getting more expensive. So you can see that although we are trying to shrink the transistors, we are trying to incorporate more functionalities per chip, but we are also imposing a cost on the fabrication plants. So ultimately everything is coming at a price. And if we can just connect this to the video which I have shown at the beginning of this lecture by Samsung Foundry, where they are commenting on the multi-bridge channel FET. So where you can see how they are stacking those particular layers vertically instead of going laterally, just to minimize the area. So that is more important here. So the invention is only important if it is useful. So if you are trying to develop something, or if you are trying to analyze something in your research, so try to make it useful, at least for people who will be studying it a few years later. So even if it is theoretical, try to make it useful for people who may derive some facts out of it, instead of making the research repetitive. Okay, so that's my point here. And another point which you must know is the ITRS. So it is now known as IRDS. So ITRS was the International Technology Roadmap for Semiconductors. And now it has been translated, or it has been changed to the International Roadmap for Devices and Systems. So this was ITRS in IRDS in 2018. So they proposed a few novel devices and structures. You can see on the left-hand side of the screen. And on the right-hand side, according to ITRS 2013, they predicted some of the very viable devices, which you can see. And they also predicted the number of years which it will take, which these devices will take to mature or to move into production. So therefore, whenever engineers, they try to design, or say researchers, they try to look into new devices, they always try to go in line with the IRDS. Okay, so that you are trying to, you are keeping match with the steps of the industry, and so that you can propose something which is not already outdated. So therefore, the IRDS is a very important document which you need to go through. And I think the IRDS now comes under IEEE. So if you have an IEEE membership, you can access the IRDS documents. Okay, and now before proceeding to the short channel effects, we always try to understand a MOSFET from its output characteristics, the linear region, the saturation region, from the ID VDS curve, or the drain current versus drain voltage curve. But there is also another important curve which is usually explored while understanding new devices. So for a device engineer, it is not only necessary to understand the output characteristics, but more emphasis must also be given on the transfer characteristics of these MOSFETs. So you see on the screen on the left-hand side, PMOS and NMOS ID VGS. Of course, they must be at different W/L ratios because of the mobility factors for holes and electrons. But you can see a symmetric IDVG for both the devices. And first question here is, why do we need a symmetric curve? Because whatever you are operating now are everything in digital domains, right? Your devices are employed in your memories and in digital circuits, in your digital logic. So whenever you are doing something in the digital logic, then the CMOS comes in, the complementary metal oxide semiconductor circuits. And whenever you have a CMOS version, it means you will require both the PMOS and the NMOS types. And it is a very major criteria that both must be symmetrical, or ideally they must be exactly symmetrical if you are to build a very suitable CMOS circuit. Therefore, on this particular diagram, you see this. These are almost symmetrical or mirror images of one another. Now, here there are a few important factors or terminologies which are used to understand the low power performance of a device on a macroscopic level. So we are not going into the device exactly the microscopic level of traps and the different phenomena of charge sharing and everything. We are trying to look at this device from what it is trying to say from its characteristics. So this is what you measure for your device on a particular instrument or an analyzer. And then you are trying to see how that performance depends, or what is the performance of that particular device. So if you see, we have plotted a logarithmic of the drain current and versus the gate voltage, right? So the first point, you plot a logarithmic plot whenever you try to see the various changes, or you try to see the orders, the minor orders which are present in your plot. Okay, because it gives a wider view of every step of current or every order of current which is changing. Now, secondly, the off current. So whenever we call the off current of a particular device, particularly a MOSFET structure, so it is usually measured at a gate voltage equal to 0 volt. Okay, so whenever we are, if it is just written that there is an off current for a device, so it is at VGS equal to 0 volt, right? And the on current of the device. Now remember, your on current of the device, the definition is valid in your super threshold region. Okay, so super threshold means you're after the threshold voltage. So anywhere your device is on, but if you are referring to a device and you are calling something as the on current without mentioning the voltage at which you are measuring, so it by default means that you are measuring at the maximum gate voltage of your measurement. So that is the on current by default. And if you want to refer to an on current by the gate voltage, so you'll have to mention that particular gate voltage. Okay, and then we have the threshold voltage. You already know about the threshold voltage. The threshold voltage gives a transition from the weak inversion into the strong inversion of the MOSFET through the obviously the moderate inversion region. So it gives a translation from the subthreshold to the super threshold region. And there are various methods of again finding out the threshold voltage. Some use the constant current method, and there are, if you look into a paper, you'll find there are 14 different methods of finding out the threshold voltage. And the threshold voltage of a MOSFET can be different based on the application you are trying to use it for. So then the definition of that particular threshold voltage, it changes according to the application. So we'll not be discussing that here. Here we are restricting it to the device level, but you must know that the threshold voltage can be defined as per your application. For example, suppose if I say I will be selecting my threshold voltage at the gate as the gate voltage at which my drain current is equal to say 0.1 microampere. Okay, so it means at that particular current you will be whatever value you get on the gate voltage curve, so that will be your threshold voltage. So many applications, they modulate their definition of threshold voltage in order to make it a very viable and useful component while describing their product. Okay, and finally the subthreshold swing. So subthreshold swing is actually a measure of how well your MOSFET can be switched off. So basically it is measured in millivolt per decade. So millivolt is the gate voltage here, and per decade means it describes how many orders of current it is moving while coming down from the on state to the off state. Or you can say that the amount of voltage, gate voltage, which is required to move the current by one order. So if it is at 10 to the power minus 6, and suppose this point it is 10 to the power minus 6, and for example you are coming to 10 to the power minus 7, so the amount of gate voltage which is which this particular distance of current covers on the gate voltage is actually your subthreshold swing of that particular device. And for MOSFETs, the subthreshold swing is limited to 60 millivolt per decade. So this is related, this is also known as the thermal limit for MOSFETs, the KT by Q limit for MOSFETs. So for MOSFETs, the subthreshold swing cannot decrease beyond below the 60 millivolt per decade. Therefore, the researchers and the industry are on the lookout for devices which can have a very lesser subthreshold swing. So the lesser the subthreshold swing, more ideal is your device for low power applications. So these are the different terminologies and components in your particular device or in a MOSFET while understanding the transfer characteristics. And if you compare two MOSFETs, you can easily compare them on the basis of these particular parameters. Okay. Now, short channel MOSFETs. So we'll try to simply know it, what is a short channel device or a short channel MOSFET. Now, in order to understand short channel MOSFET, you need to know what is a long channel MOSFET. So that's where the comparison comes. So the first point, as you can see, your device will be a short channel device. On a very layman sense, your device will be a short channel device if the channel length is comparable to the source drain depletion widths. So it means, so here, if your channel length is so small so that your source and drain junction depletion widths in the channel, remember that your channel is very lightly p-type dope if you're taking an n-channel MOSFET. So it means most of the depletion width will be extending towards the lightly doped region, right? So it's a p-n junction you are forming. So for example, here, this is a p-n junction here. So this is an n plus junction, which is a very highly doped junction. So the depletion width will be very less here. That's the property of a p-n junction. And the depletion width will be more in your channel part in this particular region. So therefore, if this depletion widths, if you add up this depletion widths, you will find that it holds a significant percentage of the entire channel or the distance between source junction and the drain junction. So in that case, your device can be called a short channel device. Okay. Now, what happens when, why are these short channel MOSFETs, why are we studying this? Why are they so important? So the gate starts losing its control over the channel. Okay. So that's why short channel effects are more important. The concept of charge sharing appears. We'll discuss this concept because this concept is the only particular topic which will clarify your doubts about the short channel effects. Okay. That is the basis of all the short channel effects, or say maximum of the portion of short channel effects in MOSFET. And the threshold voltage will be affected and other effects become predominant. But the most important point here is the gate losing its control over the channel and the concept of charge sharing. Okay, so here I have made two diagrams, very simple diagrams, because I did not want to use the diagrams from the text because they were involving too many parameters. So I tried to draw this myself just to have a very rough overview of the short channel devices. Okay, so on the left hand side you see a long channel device, obviously, because you can see that the yellowish part of the channel is longer than the yellowish part in the right hand side of your screen, which is a short channel MOSFET. Okay, now here you can see here two terms, L and L dash. Okay, so L is the total channel length of this device, so it is measured from source to drain, and L dash is the effective channel length, which means it is measured from excluding the source and drain depletion. So my source depletion ends here, so from here I will be measuring this. And if you see the difference in L and L dash is not much for a long channel device as compared to a short channel device. So if you try to find out the percentage, you will find that this difference, if you add up these two depletion regions on both the sides of the source and drain junctions, you will find that it is only a very less percentage of the entire channel length L. But in a short channel device, you will find that these portions which we have ignored, means L minus L dash, is actually very significant as compared to L dash. Okay, so therefore that is the prime difference between short channel device and the long channel device. Now coming to the point of charge sharing. Now in a long channel device, if you see, you can see that this drain or the source region or the drain region will have some influence over the depletion region. So some of the electric field from the drain will try to end or terminate on the depletion region just close to it. Okay, so it means whatever was effectively under my channel length L is somewhat controlled by this particular drain and this source, right? So L minus L dash, which is a sum of these two regions, are actually now controlled by the source and drain. But since the percentage is very low, so I can still say that the action of my gate on my channel is still predominant. Okay, so the gate comfortably can control the channel now, right? So therefore we do not have any problem in a long channel MOSFET. Now come to the short channel part, the short channel device. So here also the drain, some of the electric field for drain will terminate on the depletion region just close to it in the channel. But you must remember, since this depletion width is very comparable to my short channel length, so therefore the drain will also have some influence on the charges which are present below the gate. So if I'm looking at a picture excluding the source and drain, so what I ideally need is that the gate must control everything which comes in my length of L, okay, which comes in this length which is described by L. So the gate must ideally control everything. But now I see that some of these charges are controlled by the drain. Controlled by the drain means it is captured by the drain, by the electric field. Okay, so therefore now this drain will behave as similar to a gate. So if I put a voltage on my drain here, it will start affecting the threshold voltage of this device. Okay, it will try to bend the barrier in a similar way as the gate. Therefore the drain and the gate become comparable. But that was not the objective of designing a MOSFET. The objective of designing a MOSFET was that my gate must be the sole control. I must have the sole control over the channel. The channel is the most important part where you have your inversion. Now the gate is losing control over the channel because the drain is also occupying and the source is also occupying some of the carriers or charges in that particular length of L. So therefore in short channel devices, the charge under the gate is shared by the source, drain and the gate. So that is the concept of charge sharing. The charge sharing is very minimum here because the gate length is so large that most of the charges are controlled by the gate. So we can ignore the charge control by the source and drain sides. Okay, so that is the idea, and basically in textbooks this idea is not is covered only when you encounter threshold voltage roll-offs. But I feel that this concept must be given directly at the front start of this short channel effects, because it opens newer windows into the particular things. Okay, so therefore this is one of the most important concepts for charge sharing. Now these are some of the short channel effects. I have not covered everything here, but I am just trying to give a pictorial representation of the very important ones. The first one you see is the impact ionization. So you must know that whenever the electric field increases, since it is a short channel device, so the length, the gate length or the length over which the electron moves from source to drain, it has reduced. So your electric field, average electric field increases. So any electron moving from here may collide with the atoms and then generate electron hole pairs. And the holes may now move into the bulk. Okay, so since it's a very high electric field here, there is a presence of high electric field here, so it may be an avalanche effect which is caused in and around this junction. So it will lead to very high generation of these holes, which then will be attracted towards the bulk terminal. So then this impact ionization, it gives rise to a very high leakage current through the device, and this is usually measured by measuring the substrate current or the bulk current of that particular device. So this is also a short channel effect which we need to look through. Okay. Second one, the drain induced barrier lowering. So we'll be taking this up in the next slide in detail, but it is a very good pictorial representation here. So on the left hand side, what you see is that you are increasing VG. So you can see there is a very transparent dotted structure, and also there is an opaque dotted structure. So this refers to the short channel device, and the longer one refers to the long channel device. So if you are applying gate voltage, so then you do not have much difference in the barrier from source to the channel. So this is my barrier from source to channel. So you don't have a change in the barrier height. Now if you are trying to apply a drain voltage, now remember the charge sharing, the concept of short channel effects. In the concept of short channel effects, the drain now holds a control over your channel. So this is how this can be better explained. when you impose a voltage on the drain, so these bands will bend down on the drain side. Okay. Now in a long channel device, this point, this drain junction is very far away from your source barrier, source side junction. So therefore it will not have any effect on this barrier height. But for a short channel device, if you pull this particular down, it's like a rubber band. If you pull this down, if the distance is very small, then it will also have an impact on the height of the barrier on the short channel, on the source side. So it will effectively reduce the barrier height. And this barrier height, if it is reduced, so it means now the electrons in the source, in the n-type source, sees a very small barrier to cross over. So therefore they can easily cross over this barrier, and therefore the threshold voltage reduces. Okay, so if you look into the entire phenomenon, you will observe that due to an application of this drain voltage, my barrier, source side barrier has reduced, and due to this the electrons see a very less barrier, and therefore my threshold voltage of that particular device decreases. So that is the effect of drain induced barrier lowering. We will take up the concept in the next slide. And finally, you have the Hoque carrier injection effect. So if you are having an electron moving from the source side and it is having a very high energy, so it also has a probability to escape into the gate oxide through the traps, and then it will try to damage that particular oxide as it gets trapped there, and it tries to affect the reliability issues of that particular device. So usually the term Hoque carriers are used whenever the energy of your carrier is very high. Actually, it is related to the thermal voltage. So whenever your electron assumes a speed which is equivalent or say very comparable to a very high velocity or very close to the thermal velocity, so therefore it tries to attain a very high energy. So therefore these are known as Hoque carriers, because this is somewhat related to the thermal effect. Okay, so therefore these are some of the short channel effects which we have seen. And now let's try to see what is DIBL and how it is measured in your MOSFETs. So we have already shown this diagram here for the drain induced barrier lowering. So I'm taking this up again here. So you can see you have the long channel device and the short channel device, and due to the drain voltage this decreases. But what does this particular effect, how is this pronounced on your drain current versus gate voltage plot? So if you see on the right hand side, you can see if you measure your MOSFET at two different voltages, say you are measuring at a very low voltage, drain voltage, and you are again measuring the current at a very high voltage. Okay, so if you see a shift in your sub-threshold regime, so it means there is a shift of threshold voltage of your particular device. So it means there is some amount of DIBL effective. So if this distance is very large, or say this value which you see, del VTH by del VD. So in this case, del VD will be 1.5 minus 0.1, which is say 1.4, and say my del VTH is say around 0.1 volt. So then you can divide it and get a value for DIBL. So if you see here, let's try to see how this is related to this energy band diagram. Say I am measuring my drain voltage at a very low value, at a low voltage. So in that case, whatever this drop in my N-type drain region in the energy barrier, it will be lesser as compared to 1.5 volt. So if it is 1.5 volt, this band will be suppressed more downward. So the difference will be more. And if it is suppressed more downward, now look into the short channel device. So the barrier which the electron sees will be pulled more downwards. So as a result of which the threshold voltage will reduce. Therefore, for 1.5 volt, you see a very less threshold voltage as compared to 0.1 volt. So basically, here, if you see on application of more VDS, your barrier in the drain side will go down more, resulting in more decrease in the barrier at the source side, as a result of which the threshold voltage will reduce. Okay, so this is the concept of DIBL, and this is the way in which you can extract from a simulator or say from your fabrication results, and then give a measure through this particular metric which is shown on the screen. Okay, and finally, one of the most important points here, the threshold voltage roll-off. So the threshold voltage roll-off refers to the decrease in threshold voltage whenever your gate length reduces. So it means if you are shrinking your device from a long channel device to a short channel device, your threshold voltage will reduce. So this is exactly according to the charge sharing concept which we have discussed now a few minutes before. So because now the drain controls the charge in my channel, so you will need very less amount of gate voltage to induce the same amount of inversion here, because that most of these negatively charged ions or carriers are now controlled by the drain. So you'll need very less amount of gate voltage to map the particular charges which are present underneath it. So this is just like a capacitor, right? The gate oxide behaves as a gate capacitor. So on one side you have the metal or the gate material, on the other side you have the channel. So if you put a positive charge on the gate, the same amount of negative charge will appear just below that particular channel. So that is the concept, very easy concept of a capacitor. Now, out of those negative charges, some are now being controlled by the drain because of this significant increase in the percentage of this depletion width as compared to the channel length. So therefore, now you will need less amount of charge on the gate because there are fewer negative charges present in the channel to map this particular gate voltage charges. So you'll need a lesser gate voltage to cause a conduction of carriers through the channel. Therefore, you can see as you reduce the gate length, so you will find the threshold voltage decreases. So this is the graph for different substrate doping concentration. Okay, so this can be explained, this drop why it increases, this can be explained with the help of the expression for threshold voltage roll-off, which I have not shown here because it again will require a detailed derivation of the different components. Okay, so now we'll move into the pre-final topic of today's lecture, the memristors, which are again one of the wonders of the semiconductor industry. And these are mainly used for memory applications because they exhibit dual resistance states. So we will try to see into the memristor. So this is the principle of memristor. Just try to follow this very brief animation here. So usually we have this voltage, current, flux, and charge. So these are the four parameters which we are very commonly associated with, right? And if you can see, each of them are related by a single differential operator. So if you look into this voltage and current, say for example, so you can find that resistance, you will find the resistance if you see a differential relationship between this voltage and current. Similarly, for capacitance, you can see it is dq by dv, and for the inductor, it is the differential of the flux with respect to the current. So by looking into this particular relationships which we see, so there must also be something which gives a relationship between your charge and the flux, right? So there must be a component which must give this particular relationship. So that particular relationship is given, this missing relation is given by the memristance, which is given as the differential of the flux with respect to the charge. Okay, but unfortunately this was not discovered earlier, although it was proposed earlier, and it only came into a very it only achieved wider interest in 2008 when HP first fabricated the first memristor. Okay, so we'll look into that. So here, these are the interesting facts. This is Leon Chua, the postulator of memristor. I call him, he's called the postulator because he proposed the missing circuit element. He gave a theory, as we have seen here, that the missing link must be memristance between charge and flux. So this is Leon Chua, and he proposed the memristor as the missing circuit element in 1971. Okay, so he gave the first description that there must be another element which relates charge and flux. And in 1976, he extended this concept to devices and systems with his student S.M. Kang. So what they did, here they just tried to say that there must be a missing circuit element. And here they tried to generalize that concept to any device and system which can be built with that particular concept. Okay, so this was in 1976. But nothing was realized in physical form or in device level until 2008, when HP Labs first made the first nanoscale memristors. So you can see how this timeline has been processed over a very wider range of historical timeline from 1971 to 2008. And after that, this particular area got a major boom in the semiconductor industry because of the very conventional way or the very convenient way of fabricating this. These are two terminal elements. So therefore, you don't have much cost in fabricating these elements. Okay. And even before 1972 and after 1972, there were instances of memristive behavior in experiments and systems which were not termed as memristors. So what I mean to say here is that Chua realized, and he reported in one of his papers later, that even before the theoretical description of memristors was proposed by him, there were many experiments in which similar behavior were observed, but the people did not know or did not try to relate it to the charge and flux. They were doing a specific experiment, and those results were a part of those particular experiments. So this is how interesting the domain of semiconductor devices is. We have seen how Lilienfeld went with the patenting of his field effect device, and later on we find the field effect device was rejected for the point contact and the junction transistors. And here also we see how Chua postulated in 1971, and it took I think more than 30 years to realize this particular memristor in the nanoscale range, right? And now we'll just try to look at the working. Basically, this is not a, I cannot show you an animation. We'll see more on NanoHub right after this. But here, this was the diagram. The first one on the left, using doped titanium oxide and undoped titanium oxide. So this was the first memristor which was fabricated by HP Labs. So here you can see there's a variable written here. So actually this region, this interface between doped and undoped, this region moves as you apply voltage. Okay, so therefore this is a variable here. So this is like a p-n junction, but here the junction moves. So it is very interesting because if the junction moves, it means you will be having different kinds of resistances at different points of time. So therefore, this is a dual resistance state device or multi-state devices as reported in some experiments. So this is a very simple linear ion drift model, and this is the best model to start understanding a memristor. So if you see on the right hand side, this W is your variable and D is the length of that particular memristor. So the ratio W by D will change with the application of this voltage, because if this junction moves, or say this interface moves, so W will also change. If it moves towards the doped side, W will reduce, and if it moves towards the undoped side, so your W will increase. So as you can see, if you have a complete undoped region, so it will refer to an off-state resistance, and if you have a complete doped region, so you will have an on-state resistance. So your resistance will move between this R on and R off. So it will vary between this R on and R off. It is like a variable resistor, right, using the semiconductor materials. So it is pretty interesting because with the application of a voltage, you are trying to modulate almost something which looks like a junction between two materials, right? So this is one of the most phenomenal discovery in the history of devices. And you can actually relate the voltage and current of this memristor. So xt here you can see is the variable, Wt by d, and we are mentioning it as a dependence of time because you'll have to apply a time dependent voltage here. Although you can observe the same states for DC, but it is recommended that if you apply a time varying signal, you can observe the memristive behavior quite clearly. And it should be operated at low frequency because at high frequency, your memristive behavior will lose its property of hysteresis. Okay, so we'll try. I will show you an example on nanohub if time permits, right? And memristance is defined exactly as you define a resistance. So it is V by I. Okay, so you can also view this memristance, how it will look for a time varying waveform on nanohub. And these are the properties of memristors. These are pinched hysteresis actually. So pinched hysteresis means you have come across hysteresis plots, but pinched hysteresis means that it will have to cross at some point. And basically, what Chua proposed is most of them are pinched at the origin, right? So earlier it was found that it was pinched at the origin of your IV characteristics. But later on, people have reported experiments where there were shifts of this pinching point, but still the basic criterion is that it has to be pinched somewhere in your hysteresis. So these are some of the examples of how the current versus voltage characteristics look for a memristor. Okay, so this is an application of food protein sensor using memristive action, and this was designed by us and 2 students who were working under this. And this basically, it was we saw that the memristive action is very predominant in proteins, and it has been reported in various animal proteins, silk proteins. So we tried to extend this into food protein and try to make it as a sensor. Okay, so you can see there's a function generator here to generate that time varying waveform of low frequency, and we have an oscilloscope where we can measure that signal. Okay, the output. And we have used the resistance so that we can read the voltage at this particular node. And the sample holder, you can put various proteinous substances. We tested with milk, the container milk which we get, and also we checked with the chicken egg albumin. So we found very interesting results, and we were able to develop a few mathematical parameters. Okay, so but before that, we had to be confident that the proteins were very much useful in detection of this. They exhibit this memristive action. So we denatured that protein. So denatured means you'll separate the protein from the entire mixture, and we tried to see the waveform. So the concept of memristor says that if there is no memristive material in your particular system, so you will have linear plots. So you'll have straight lines in your output characteristics, which you see on the right hand side in figure B. So this is after the proteins have been filtered out. You see exactly linear plots here. And if there were proteins, which means before the process of separating the proteins, you will find that there are non-linear plots here. So we were confident that we can proceed with detection of food protein. So this was just a test to show, and it is very interesting to see how with the absence of proteins, you can see this linear plots here. Okay, and these are some of the characteristics which show at say 103 milligram per milliliter and 32 milligram per milliliter. So for 103, you can see the slope, the non-linearity is high. You can see the peak value has also reduced for the voltage across the sample, and for 32, the peak value is still higher. Okay, and you can see the hysteresis in the first plot A, figure A, where you can see there's a pinch off point exactly at the origin for our plots. So this confirms that protein in food can be used as memristors. Okay, so now I will show you what to do on nanohub, or how to access the nanohub profile. This is the last part of this lecture, and the reason, first of all, let me tell you the reasons why I'm showing you this. Now, when you see, you will have many licensed tools everywhere, and each tool costs very high, right? So basically, if you are trying to buy the license for a tool, for a software, so it is very high in terms of Indian currency. So basically, almost the same things can be done if you try to use a free tool or an open source tool. And NanoHub is exactly the right spot where you can access those tools and try to understand many concepts of semiconductor devices and explore actually what are the things going on in the industry. You can build a SPICE level circuit in NanoHub. You can look into the bioinformatics. You can look into the devices, the Fermi levels. You can build a PN junction. You can see a memristor. So there are plenty of tools on NanoHub which you can explore, and you can even use them in your research. And people have done them. So people have explored this in their research. So therefore, I'm going to show you this, and it is exactly free of cost, and you can access it from your homes. So that also gives you the liberty of not using a licensed tool and getting this almost the same facilities on NanoHub. Okay, so I'm going to share you the screens for this NanoHub. Hello?
Yeah.
So I think you can see the screen for NanoHub here. You can see the screen. So this is the NanoHub portal. You can type nanohub.org to access this portal. Okay, and you can log in using, you can create a free account and log in into this website. And after that, you can go to resources, and then you can move to tools. Okay, so you can move to tools, and after that you can access the different materials which are present. So I'll try to show you the tools which are present on NanoHub if the internet supports. Okay, so we are pretty fine with the internet. So here you can see there are plenty of options. So there's a tag here. Using the tag, you can, suppose you click at a tag, you will see the different tools on in the middle part of the middle pane of your screen, the resources, and from there you can easily use them. Okay, so I'm clicking on all, which activates my window for all these resources, and I will try to move into the memristor part. Okay, so basically they are listed in alphabetical order, so it must not be difficult for you. You can see there are plenty of tools here, right? And I will move into this memristor simulation tool here. Okay, so once I click on this, you can see this launch tool option will come, and below that you can also see the different key parameters. Say 1145 users have used them. There is one citation, and somebody has asked 2 questions here. So if you click on launch tool, it will directly open up that particular GUI for the memristor. Okay, so let's wait for some time. It will load that particular tool. So this is the interface or the screen for your tool, which you can see. Okay, and probably this uses the very basic model which I have discussed, the linear ion drift model. Okay, and if you look at the bottom part of the screen here, you can see you can define your on resistance and off resistance here. So you can change these values here. Okay, so presently the on resistance is less because it will refer to high current. It is in the on state, so it refers to as 100 ohms, and R off, or the off state resistance, is 16 kilo ohms. And apart from that, you can also select the properties, the average carrier mobility and the device thickness. So presently I am not trying to change anything here. I will only show you how to see the outputs on the screen, and you can set the frequency. It is at a very low frequency, and the amplitude of the applied signal is 1 volt. Okay, and so you can see a simulate button here. If you click this, the simulator will run, and it will give you the current and the voltage plots. So this is the voltage pulse, and interestingly, you can see the current wave. So this is the current wave which you can see. So the peak reduces if you see, right? And this is due to, from here you can also find out the memristance fraction, which is W by D. So W by D looks like this. So the idea of showing you this is that you can actually analyze similar things on NanoHub. And suppose you want to understand memristor, so you can take your pen and paper and try to solve the linear iron drift model and try to compare with what is present on your particular simulator here. Okay, and remember, you can terminate here by clicking this option. This tool will be terminated as of now, and you can recall this later and you can select it. Okay, and all your sessions will be recorded here, so it will also display the time, and in this way you can access all the tools. And apart from these tools, you have many online presentations, mainly downloads and presentation materials, papers, some series, teaching materials, and workshops going on NanoHub. So this is a very useful platform to be explored, and it gets updated from time to time. So every now and then you will have newer tools in the database of NanoHub. Okay, so that's the idea of showing you this NanoHub, and you can explore lots of things here. Okay. So now we'll just move into the conclusion of today's lecture. So what we can do actually from this particular lecture, what you can take home from this lecture. So as I had already said at the beginning of this lecture, we are not here to discuss a very technical, very deep technical aspect of devices. We are here today to only understand how to look into the nature of devices. What are the different parameters? What are the different forms of investigation? The different perspectives which are required to look into a device. Okay, so that is what we are here for. And as I have said, instead of focusing on quantitative aspects of devices, you always try to find out a qualitative explanation for that particular phenomenon. So if you are equipped with a qualitative explanation and a quantitative explanation, then it means you are ready to explore the semiconductor devices at any level. Okay, and secondly, websites like NanoHub, they help you to study things by yourself. And there are many things actually. Whenever you are going through a textbook, the figures or the diagrams are static, so they do not move. So if you are changing a voltage, you need two different figures to show you the difference in the inversion charge. What if you can visualize this in an animated form or in simulated form? So this can enhance your learning abilities. So therefore, you must explore this device or this particular website. And you can check efficiency of different models, as I have tried to say, and try to find out if you see some drawbacks. Suppose you find an application where this particular device may not work at that efficiently. So you can now try to look for newer architectures, or say you can propose a newer method and then try to solve it theoretically or practically through the simulators. And finally, the most important point, which I try to focus in every lecture or interaction with students, the device circuit integration is very, very important. Currently, if someone is working on devices, they are working on devices alone. They are not trying to develop a model, or they are not trying to extract things which can be again implemented in a circuit and checked. So therefore, this is a very wide area of research, and you can work at it from any level which you have, even from the level of SMICE simulators. Okay, so with this, I end my lecture here, this webinar. I thank you for your patience, and I also thank the organizers. But before ending it, I have a few acknowledgements to make. So these are the teachers and colleagues to whom I am indebted to. Apart from this, there are many colleagues which I could not put everyone's name on the list. And there were students who are the backbone of every research which teachers do. And finally, an acknowledgement to SIR for funding a project on which I'm working. So I thank the organizers and the professors of Madnapel Institute of Technology and Science for giving me this opportunity. You can put all your questions in the WhatsApp group, which I think Mr. Dr. Hoque has created. So you can put all the questions there, and instead of answering them here impromptu, I will try to answer them one by one in details in the WhatsApp group. So that will be actually more beneficial for you, because here I'll be taking up many questions in a very shorter duration of time. So therefore, I will try to answer them in a very detailed way in the WhatsApp group by today. Okay. So thank you, everyone. I transfer the proceedings to the organizers. Thank you.
Okay, thank you, Rupam Goswami. Hello.
Welcome. Yeah, my pleasure.
Yeah. So, Dr. Sarwesh. Hello.
Yes, sir. I am there. Yes,
Yeah.
sir. Actually, Dr. Rupam Goswami, I feel the semiconductor basics and what you thought is really a basic, as well as it is definitely needful for all the students who are studying now in BTech and who are listening this video. And one more important thing I want to say is, I thought, sir, Dr. Rupam sir will go much deep inside and in particular specific stuff like that, but he said very basics in a very clear manner. Even who doesn't understand anything about the devices basics, semiconductor devices basics, he will be understanding very effectively and very clearly, sir. Even I too.
Thank you.
I hope the information you shared regarding the Nano Hub and other things, it will be really useful, sir. And the attendees who attended, really, I hope they will be highly benefited in semiconductor basics. And your lecture says how you are deep, as well as you are clear about the semiconductor basics. And it's a very great opportunity for our MITS faculties, as well as MITS college students to get your lectures. We are happy really we are happy to get your lecture. And we hope every students might got a clear idea about semiconductor physics. On behalf of Madanapalli Institute of Technology and Science and EC department, head of the department, and Dr. Shanidul Hoque and myself, we all sincerely thank you for giving such a wonderful lecture on semiconductor physics.
Thank you. Thank you so much.
Thank you.
Shall I close the session, sir?
Yes.
Andy, sir?
Yes, sir.
Shall I close?
Sir, yeah. Also, I want to thank Sir Dr. Hemant sir for your effort.
I want to sincerely, I too forgot. I want to thank Dr. Hemant sir, who made everything possible and made this live event successful.
Thank you, sir.
Thank you.
And